we would like to present the collaboration that we did together, which is about RISC-V customization after a tape-out. So you can think of customization that you need to do when you have a silicon. So the agenda is as follows. I will try to sketch the business case or why we are actually talking about this problem, then go through the solution that we put together, and we will conclude with some case study by example showing the capabilities of such a solution. But first, let me just go really quickly through company introductions. So as I mentioned, I'm from Codasip. Codasip is a leading provider of RISC-V processor IPs. So we have a wide range of selections, starting from the embedded cores up to the application class, CPUs running in a cluster. And we have a tools, EDA tool, by which you can customize them either at the beginning of the design process or after the tape-out. We will kind of dive into it in a minute. We are based in Europe, and one of the things that we are promoting is the heterogeneous compute or custom compute, because we believe that it drives innovation and differentiation. Menta is pioneering the e-FPGA design for more than 15 years. They are also based in Europe, but they have the presence around the world. And we will learn about the e-FPGA in a couple of more slides and why it is important to have such a technology. But now let's look at the business case, or why we are actually talking about the problem today. So as I mentioned, the heterogeneous compute is quite popular. And if you look at the agenda of this summit or previous summits, you will find out that many talks actually are about the heterogeneous compute and how important that is, because of maybe the performance improvements that you need to have, or maybe you would like to have a solution that generates small code size because you are in the embedded world. There are many, many different use cases why you would like to do that. And if I would like to be a bold, or let's say maybe even controversial, I can say that any ISI extension that RISC-V has at the moment, at some point in time, was custom extension. Custom extension is usually done at the beginning when you are designing the processor by architects, because they know the field, they know the domain they would like to attack. And this is kind of thing that we can see, and we heard some nice examples in the morning keynotes. But there might be use cases where you are not able to do this because maybe the field is not that well known, or maybe because it's rapidly evolving, like AI, where we have different needs every few months. Or there could be a device like in the industrial IoT, where you need to have a device up and running for 5–10 years, and you will never know whether the standards will shift or the security requirements will shift, so you need to adopt that. And the technology that we used to solve this problem is RISC-V, obviously, because this is well suited, thanks to the fact that this is extendable, and e-FPGA that allows to put the logic after the tape-out. So let's look into that in a bit more details. So we need three major components, and we will go quickly through them. So RISC-V processor is obvious choice, right? And in this demo, or in this use case, we are using the L110, which is one of our processors. It's embedded, highly configurable core with configuration on the ISA side, but also on the microarchitecture side. But more importantly, if you look at the picture, we will see this e-FPGA over here that is really smartly integrated into the design that allows then the customization in the field. And we will talk about the integration in bit more details later. So this is the first piece of the puzzle. The second piece of the puzzle is a tool by which you can do this customization, the tools in which you design your instructions in a highly automated way. Sure, you can do it manually, but the more automation you have, in the better shape you are. And we use Studio Fusion, which takes the custom instructions in the form of the high-level description language, which we call Codal. And then Studio generates not only the RTL for the custom instructions, but also test benches, compilers, and so on. So it gives you the whole set of it. So the automation and the Studio in particular case is the second piece of the puzzle. And then we have the third piece of the puzzle.
Okay, so let's talk about e-FPGAs and what they are. So you're mostly familiar with FPGAs, which are standalone devices. And they both have reprogrammability through the bit stream, and we have tools to convert RTL into the bit streams. The e-FPGAs and FPGAs have basically a commonality, so we'll talk about the actual commonality first. So If we look at the block diagram on the right-hand side, we can see we have embedded logic blocks, which are basically like ALMs or CLBs or slices in an FPGA vendor's technology. We have DSP blocks, which are multiply accumulate blocks. We have block memories. And then we have clocks and the configuration interface, which is how you program it. The I/O bank is where things change. So at the I/O bank, inside an FPGA, you have bond out to pins, which are basically driving highly capacitive loads, and usually have SerDes and other technologies there to actually improve the speed. In an e-FPGA, which is inside your SoC, we have an I/O bank, which is basically working at wire speed. So the wire speed gives you large bandwidth, and we also have the ability to have very, very broad or wide buses because it's inside the silicon. So you can size an e-FPGA. Basically, you can shrink down the mix of technologies. So you can have different LUT and DSP and RAM mixes. And then it has a better power profile because you're not using the I/O structure inside the FPGA, which is basically burning a lot of power, driving the capacitive loads. So another big advantage of this is it's usable in your node for your technology. So an e-FPGA, in our case, is using standard cell technology, so it fits straight into your design flow and your ASIC flow. Next slide. Okay, this is a quick overview. I don't want to belabor this slide. So this is really showing where the RISC-V and e-FPGA are mixed together. And then we have other technologies inside your SoC that could be augmented by FPGA or e-FPGA technology. Okay, next slide.
So let's look into the integration in a bit more details. So in general, we can see that we have two main interfaces over here. One, let's call it programming interface. This is the interface by which you can upload the bit streams, you can configure the FPGA, and so on. But more importantly, you have this second interface over here by which you deliver the data, such as operands, but not only data, but also some control signals that gives you the information about which instruction you would like to do there, also information about the pipeline, whether the pipeline can accept the results, and so on. So there is a tight interconnection between those two worlds with the intention of clearly separated those two worlds. What I mean by that is that we design it in a way that no matter you put inside of the FPGA, you can't break the rest of the core. So sure, you need to verify your own instructions that you put there, but you can't, whatever you put there, even if it's buggy, that you can't break the rest of the core. This is a concept that we call bounding customization, and there is a second talk about this concept later in the afternoon, so feel free to join it. For the time being, just important information is that this is the concept, that whatever you put in there, you can't break the core. You can have single instructions or simple instructions that takes few arguments and produces the result immediately. You can have instructions that take multiple cycles. You can have instructions that have states. All of it can fit inside of the FPGA in the way that you want to. And you can have as many instructions as you want as well, given to the core and the way how it is prepared. So this e-FPGA concept or this concept is not applicable only into the embedded world. You can think of also application class too, because if you wrap it nicely, then you can do it also in the application class CPUs. If you look, and what we like to showcase on this slide is the, let's say, ease of use of such a solution. Because as I mentioned, the custom instructions are designed in the high-level description language, which is called CODAL. You can see fragments over here. And we designed this in a way that we would like to hide the low-level details, such as pipeline controller or the instruction encoding. That's all of it is pre-computed or handled in a studio internal things. And what the user needs to define is just the mnemonics of instructions, how many operands it has, and whether it has a single cycle or multiple cycle instructions. So as a user or as the one who customized the CPU, you just need to provide this. And then, of course, you need to provide the behavior of instruction in the end of the day. So in this particular case, it's quite simple because it's just a matrix multiplication of size 2. But you can imagine you can put pretty much anything you want in there, assuming that it fits inside of the FPGA, of course. If you have such a design, then you click on the button, and because we have automation in place, you're going to get the SDK that consists of the LLVM compiler that's aware of new instruction, and the compiler is able to use these instructions in many cases fully automatically. So unless you want to stay in the assembly world, you can just write the C code and the compiler will pick it up. Besides the compiler, you also have the simulators, profilers, and so on. And then on the hardware side, you're going to get the RTL of such instructions in a system Verilog, which is important from this talk, for this talk, because once you have the RTL, you can do the magic on the e-FPGA side.
Okay, so quickly here, we just have the RTL coming in, goes through this magic FPGA gate cruncher, and then it goes out into the bit stream, which programs the FPGA to become the desired function. Okay, next slide. Okay, so Menta has a set of tools called Origami Programmer, and this is an ASIC flow, probably typical you'd be familiar with Xilinx and other kind of vendors. So it takes in the application RTL, and then you add constraints to it, timing and I/O, and basically it does synthesis, place, and route, and then it outputs the bit stream. So you have a simulation model that you can basically back annotate and do simulation to make sure you have functional equivalence of what you need, and then you have timing reports telling you whether you meet timing or not. It's a GUI interface to start out with, and it shows you all the resources that you can use. And once you're done with that, you typically go through this iteration a couple of times through your GUI interface as you're figuring things out, and then you can fully command line script it. And that can be all push button automated behind the hood. Okay, next slide.
So as I mentioned at the beginning, let's look at one of the things or case study that kind of proves the capability. This is by no means the best custom instruction for the multiplication of the matrices, and also the code over here is not the best one we can find, but it kind of proved the point. So when we kind of look at this code, we said, okay, well, let's create a single instruction that would accelerate such a design, and that kind of do it after a tape out. So what we did is we modeled a new instruction like this. You can see that we have one destination and we have 4 input operands. 2 of them are hard-coded. So we just selected 2 fixed registers and 2 that you can kind of configure on the compile time. If you actually saw the instructions in the previous slide, which was that simple, you just need to multiply it and accumulate a few numbers. We generated the SDK, we generated the hardware, and if you look at the SDK portion of it, then you will get what you would expect. So if you compile such a code, the compiler will pick the new instructions, which is what you expect, and if you have a size, the metric size number 2 of 2, then you have 4 instructions. You can see that we have 3 operands over here because I mentioned that those 2 are fixed, so you don't see them there. You can enable that if you want to, but from this presentation, we just selected not to. And this is what the compiler will do for you. And then let's look at the results on the PPA side.
Okay, so we'll just talk about the performance of this. So as you can see on the x-axis, we have basically a square law function of the matrix size. On the y-axis, we have the clock cycles. And you can see it's kind of linear, which is a good sign. It means that it's basically optimizing to be using the hardware. So as the speed up is higher, the matrix gets bigger. So it's actually, we're getting an improved performance from the use of the hardware. Okay, next slide. Okay, so this is just showing you the e-FPGA resources and what the reality is. I'll go on to the right-hand side here just to talk about the actual the example here. So we're using about 12.7% in logic, and we're using about 75% of the DSP resources. We actually have 12 DSP blocks in here. So we actually honed this design so that we're actually using mostly a DSP-centric design. And that gave us the best optimization for size and speed. And then you have a choice of whether this is a synchronous or an asynchronous design. In this case, we chose asynchronous because we wanted to do a fast turnaround in the clock cycle so that the CPU can clock it through very quickly. But if you have applications that have very complex algorithmic stuff, you can clock it in, you have a synchronous design, multi-clock domain, which blocks the processor, but you have to do a trade-off. And this is a kind of systems design trade-off. Okay, next slide. Okay, so we'll do some conclusions here for future work. So obviously, RISC-V is extremely well positioned for innovation through instruction set architecture extension. The combination of RISC-V and e-FPGA gives you possibility to customize even after tape out, and that could be changing your design or reiterating your algorithms after tape out. Tooling such as Studio and Origami makes the process fast and efficient. So we have a sandbox you can just play in, and you can basically change things as you go. So the possibilities for future work include a multi-CPU system with a shared e-FPGA core. And we'll go to the diagram on the right here, the Hungry Hippo. For those who don't know this is a child's game, and you basically push a button and you try and grab the marbles as they come down. The hippo grabs the actual marbles. It's manic. I mean, if you play it with kids, it usually ends up in tears. So really what we're trying to do is model here that we have CPUs as the hippos. So we may have a matrix multiplier, a cryptographic, a video, and an AI hippo in this case. So the data can come along, and what we would want to do is basically make sure that there's load balancing amongst these CPUs, and the CPUs will basically have their own local domain and local memory area, and the streaming will come down from a memory pool. That memory pool could be implemented, interfaced by an FPGA, and the streaming will come through, and you could compress it or decompress it through that streaming interface. So you're basically optimizing your use of the e-FPGA, and you're maximizing the use of your CPUs. The obvious thing here is you can have as many CPUs as you want. So they all have their specialist functions. So you can actually use them as general functions, as well as you can use them as a specialist function. So there's numerous other ideas. So we look forward to your collaboration here. And we'll finish up the presentation with a Q&A. So thank you very much for your time.
How you can partition the part which is related to e-FPGA and the part would be implemented on ASIC? Is it possible to do it automatically, or that would be decided later? Thank you.
So to some extent, it has to be decided at the beginning. So you need to decide how big the e-FPGA actually is in the real ASIC, right? So this has to be decided at the beginning. And that's quite the only thing that you have to design, because the interfaces are kind of clear. The core is prepared for that. So then you might have the L110 with the e-FPGA that is smaller, because we don't expect anything bigger in there. But you can also have another iteration of it where you have a much bigger e-FPGA. But that has to be done at the beginning. So once you have a chip, you can't change the e-FPGA. Yeah.
So I can add to that as well, that you can iterate the e-FPGA very, very quickly. So we have a tool that allows you to basically generate, or we generate different IP sizes and mixes, and we can give the customer any of those mixes. So you may be DSP-centric, you may be logic-centric, or you may be memory-centric, and we can provide you all those different flavors. So then you can go and do your iterative algorithms and figure out what you need, and it's relatively quick. We can turn that around in a matter of days. Because we're standard cell, we can generate e-FPGA cores like that. Okay.
One last quick question.
Can you reprogram the FPGAs on the fly while an application is running? If you have multiple algorithms that have different custom instructions that they want to use, but they can't both fit on the e-FPGA?
This should be possible. We haven't thought about this one, but this should be possible because there is no blocker for doing such a thing.